Well, last time I would like to recall that the general theorem which we are proving is this theorem by Harrer, claiming that the curve complex is homotopy equivalent to a wedge of spheres of a certain dimension, as is written. And I have told you that we will not be careful about the number of spheres, and we will only prove a weaker assertion that actually this complex is k-dimensional and k-1 connected, where k is this specified dimension, and hence it is a wedge of k-dimensional spheres up to a homotopy equivalent, of course, to a wedge of k-dimensional spheres, but I will not be precise about the number of these spheres. However, in fact, it is as written. And last time we have proved the first part, namely that this curve complex is homotopy equivalent to a complex of to an n-dimensional complex where n is this number. So the second part is that it is n-1 connected, but the first part was proved only modular one lemma. I would like to remind this lemma. This was lemma, this one, and now I recall what this lemma says, and we proceed with proving this lemma. So if we have a surface of genus G with n punctures, where n is greater or equal than 1, so at least one puncture, then we can consider the curve complex, and inside this curve complex we can find such subcomplex C hat. In C hat we do not allow a curve which becomes inessential after deleting puncture P1. So we do not allow a curve which bounds a disk with exactly two punctures, one of which is P1. So this curve is not allowed, that curve is not allowed, and it is important that for each pair of points, in fact, there are infinitely many of such curves, so there are plenty of them which are not allowed. So these curves are not allowed here, and we consider, but it is allowed that a curve bounds exactly two punctures, none of which is P1. So this is not forbidden. So this is a subcomplex, and for this subcomplex we have a natural map to the curve complex of surface of the same genus, but with the number of punctures with one less puncture. This is just by forgetting the puncture P1, or we may say by filling the puncture P1. So this is a natural map phi, and lemma is that which we have used this lemma today last time, but we didn't prove it yet, that this phi is homotopy equivalent, is homotopy equivalence. And now let us prove this lemma. Well, how one usually proves that something is a homotopy equivalence? First, we need to construct a homotopy inverse map, and then we need to prove that it is a homotopy inverse of phi. So the construction is by a simple but very nice trick. Let us choose a hyperbolic metric. As usually, we choose a finite area, complete, hyperbolic metric on this surface with n-1 punctures. We all know that it is possible. Actually, I just would like to say that there are several cases when this is not possible. Well, this is possible only if the Euler characteristic of this surface is negative. But if this Euler characteristic is non-negative, it is not hard to see that, in fact, both complexes are empty. So it is not, there is nothing to prove in this case. So we may assume that the Euler characteristic is negative. Then we have a finite area complete hyperbolic metric. And now the trick. Well, first of all, once we have such metric, we may look on this curve complex. Usually we say that in curve complex, vertices correspond to isotopy classes of simple closed curve. Once we have a hyperbolic metric, we may say that vertices correspond to closed geodesics. Simplices correspond to, so vertices in this complex correspond to simple closed geodesics. So we do not need to think about isotopy anymore. Simplices correspond to collections of pairwise disjoint simple closed geodesics. Simple closed geodesics, and so on. So and now observation that there are only countably many simple closed geodesics on this surface. This is a simple observation. I would like to leave it as exercise for you. There are many different ways to prove this. So this is a good exercise. And now, of course, finitely many smooth curves cannot, their union cannot be the whole surface. So hence, there exists a point Q in this surface that does not belong to any closed geodesic. To a simple closed geodesic. Simple is not important here, but so we have this S, G, n-1. we have plenty of geodesics, but countably many curves cannot in the union cannot be the whole surface. This can be proved, for instance, by introducing some measure on the surface, usual volume form, and of course any geodesic has measure 0, since it is a curve in a surface, and so actually we have the set of full measure consists of points that do not belong to any simple closed geodesics. Well, choose any such point, and now we can add this point as a puncture. We can make this point a puncture, so we can delete this point and form a puncture. And then for any simple closed curve, after deleting this point, after removing this point, we get the surface of genus G with n punctures. And so any set of simple of pairwise disjoint simple closed geodesics on this surface yields a collection of pairwise disjoint simple closed curves on this surface, and hence we get the map from the curve complex here to the curve complex here. But look, of course, it is not possible that we cannot obtain a curve that encloses exactly 2 punctures, one of which is this Q. So in fact, we get into C hat, where this Q, actually this is P1. We just denote all other punctures by P2, PG, and this P1 is exactly this new puncture. So we get opposite map. We can remove there are some difficulty with words. When we add a puncture, we remove a point, and so we can add a puncture, or we can delete a puncture, adding a point. So we have these 2 maps, and now we would like to prove that they homotopy inverse to each other. In one direction, this is obvious. In fact, if we first add a puncture and then delete it back, then of course we get the same curve up to isotopy. So, well, I would like to copy this. So if we apply psi first and then phi, then this is just the identity. So we need to prove the inverse map is not the identity. Just I would like to show one example in a moment. So we need to prove that the second composition, phi first and then psi, is homotopic to the identity map. Okay, why it is not the identity itself? Actually, look, there can be such situation. So, for instance, one of possible examples. Let these 2 points be punctures P1 and P3, or P2 and P3, and this one is P1. And look on those 2 simple closed curves. this red one and this violet one. Definitely they are not isotopic, but for instance, they have a geometric intersection index 4, so they are not isotopic. But after deleting the puncture P1, they become isotopic. They are isotopic in this surface with n-1 punctures. When we insert the puncture back, this means that this red and violet curve, they are isotopic in this surface with P1 deleted. For instance, so we need to replace them. Here we have hyperbolic metric, and we replace both of this curve by a geodesic, something like that, by a closed geodesic. And now we have this choice of point Q, which is arbitrary, which is just okay. We just make an arbitrary choice. We have taken any point Q, and this point Q, depending on where, which is we have some freedom in choice this point. For instance, if it turns out to be here, then look, so the passing here is phi, we forget about puncture, and passing back, and look, we both of these red and violet curve actually goes to this curve. So this is not the identity. If Q would be in some other place, we would have some other rule, but any choice of this point Q says as certain particular rule of making a curve on SGN from a curve on SGN-1. And this rule is by no means canonical. It depends on the choice of Q. But once we have chosen Q, there is such a rule. But of course, different simple closed curve goes to the same under this mapping. So it is not the identity, but the claim is that it is homotopic to the identity.
Сейчас, вообще у нас утверждается, что если у нас есть кривая на поверхности с дырочками, то тогда у ее гомотопического класса на поверхности с дырочками есть геодезический представитель, да?
Да, мы это тоже доказывали.
Нет, это чудесно, но тогда вот, например, фиолетовая кривая, да, ее же можно смотреть как на нее можно смотреть как на кривую. Сейчас.
Well, I think I understand your question. Look, we may introduce a hyperbolic metric here.
Yeah, but a hyperbolic metric on on the surface without n-1 points is the same is automatically produces a hyperbolic metric on SGN, right?
No. The matter is that all our claims about closed geodesics in isotopic classes and so on, we have proved only for we would like to work only with hyperbolic metric, with complete hyperbolic metrics. All they are true only for complete hyperbolic metric of finite area. And if we restrict this hyperbolic metric to the surface with one more puncture, the metric is incomplete. So none of this, we may introduce here a hyperbolic metric, but it has nothing with this hyperbolic metric. It is some different. And actually, in a moment, we will introduce this metric, but it is different metric from those one. So of course, if we take the restriction of this metric, then it is not true that any isotopic class is represented by a geodesic curve. Okay. And now, now I would like to introduce the hyperbolic metric, complete finite area hyperbolic metric here. Just it is convenient to me to have hyperbolic metric is just a way to choose prescribed representatives of isotopy classes so that they are disjoint whenever it is possible to choose disjoint representatives so I do not want that these two hyperbolic metrics are somehow related to each other. It is not true. So these are completely different metrics. But at the moment, it is convenient to me to have a finite area complete hyperbolic metric here. Well, in fact, it is always not pleasant to construct some homotopy on infinite complexes. But actually, we do not need this. It is a standard fact in homotopy theory of cell complexes that suppose that we have two maps between two CW complexes, then they are homotopic provided that they are homotopic on any finite subcomplex. So it is sufficient to prove the following. Oh, sorry. It is sufficient to prove that for each finite subcomplex K of this complex, of this complex with hat, we may consider psi, well, first phi, then psi, sorry, restricted to K, and it is homotopic to the identity map on K. Now this finite subcomplex always, it is sufficient to prove this. Finite subcomplex always has finitely many vertices. Each vertex corresponds to a simple closed curve on
Почему достаточно на конечном подкомплексе доказывать?
Потому что для клеточных комплексов гомотопическая эквивалентность эквивалентна слабой гомотопической эквивалентности. Поэтому на самом деле достаточно доказывать не только на конечных подкомплексах, а достаточно доказывать, грубо говоря, на конечных подкомплексах, ну, на сфероидах. А каждый сфероид лежит в конечном подкомплексе.
Ну то есть, что два комплекса гомотопически эквивалентны, достаточно, а то, что два отображения гомотопны, не обязательно.
Сейчас не понял. No, a general fact that if we have X and Y CW complexes, if we have, oh, sorry. I'm trying to... Я пытаюсь вас обмануть, да?
Ну, и бывают фантомные отображения.
Да, бывают фантомные отображения. Yes, there are phantom maps, but look, for homotopy equivalence, this is enough. Namely, to prove that a map, if we would like to prove that a map homotopy equivalence, yes, this is only for equivalences. If this will follow if we prove that F is a weak homotopy equivalence. For CW complexes, this is the same homotopy equivalence. And this means that F induces isomorphisms in homotopy groups. Yes. And now if we prove this, then it will follow that so we have this C hat, we have phi to C of SGN minus 1, and we have psi back. So they if I prove this, then it will follow that this phi and psi induce isomorphisms in homotopy groups. Namely, any of course, since we already know that phi psi, yes, is identity, so we know that the induced maps on homotopy groups is also identity. So psi star is the right inverse to phi star, but vice versa, if we have any spheroid here, any map of any sphere, then it is always contained in a finite subcomplex. So in this finite subcomplex, phi and then psi is homotopic to the identity. If we prove this, it is homotopic to the identity. So this spheroid, well, phi and then psi of this spheroid, let it be here, is homotopic to the initial spheroid. So we have identity map. So psi star phi star is identity map in homotopy groups. Yes. Thank you very much for this question. So it is only for equivalences. For instance, if a map induces 0 maps in homotopy groups, equivalently, if a map is trivial on any finite subcomplex, then it is not always true that it is homotopically trivial. So there are such phantom examples that a map between CW complexes is homotopy non-trivial, but is trivial restricted to any finite subcomplex. But for equivalences, this is okay. For equivalences, this is true. And here is the proof. And this is a standard fact that for homotopy equivalence is equivalent to weak homotopy equivalence for CW complexes. So, okay, it is sufficient to prove this for a finite subcomplex. For a finite subcomplex, we may choose. Well, let this be the vertices of K, all vertices of K. So suppose that this fine subcomplex has k vertices, and we represent these vertices by geodesics in this hyperbolic metric. So these are geodesics. I need metric only to choose some particular representatives. It is convenient to choose particular representatives. Okay, but now we may proceed as follows. We may take well, let us go below. So once more, we have this surface with P1 and several other punctures, and we have this is SGN, and we have this surface, the same surface with deleted P1. This is SGN minus 1. And between this is not maps between surfaces, these are maps between complexes, but I still draw it like that. Okay, and so we have these vertices represented by certain geodesics. Now I consider metric here. So these gamma 1, gamma k are geodesics in metric on surface with n punctures. But now we can consider to every such vertex we can apply phi and then psi, and generally we get another vertex. We may get the same vertex, but sometimes we get another vertex, and we again may represent it by geodesics. Let this be gamma 1 prime, gamma k prime. They are again geodesics, simple closed geodesics. Yes, it is important. Well, that's okay. But now look. The main observation is that each gamma I prime is isotopic to gamma I on the right hand side in this surface with n-1 punctures. So if we delete the puncture P1, then the curves become isotopic. If we remove the puncture P1, if we forget about it, is better to say, if we forget about the puncture P1, then the curves gamma I and gamma I prime become isotopic. However, they may not be isotopic in the initial surface SGN. But okay, let us look on this isotopy, on these isotopes in more details. So let us consider this surface SGN minus 1. Yes, I always, it is convenient for me, I fix this puncture P1. So in this surface, I always have a pre-chosen point P1. It is always convenient to have this point in mind. So it is not a puncture anymore, but it is convenient to have this pre-chosen point. Okay, if I have here SGN-1 times interval, then what is an isotopy between gamma I? Sorry, I would like to take another color. This one is gamma I, And here I have some, it is just some, of course, gamma I is essential curve, but it is just some schematic picture. And what is an isotopy? An isotopy is the annulus, and an annulus here I denoted by AI. So AI is diffeomorphic to the cylinder. Circle multiplied by the interval, and it is embedded here. Preserving the level structure. This means that we have here coordinate of time, and here this coordinate, they should go one to another. So any isotopy is like that. So isotopy is by definition such cylinder. Isotopy means that our curve changes in time, and finally it is gamma I prime. Okay, and now we have many of such cylinders for any eyes, for different eyes. I just draw another one, so gamma J prime, and here is gamma J. Well, something like that. These cylinders may intersect and so on. And also one important thing is that besides of them, I also have this segment P1 times segment. I have in mind this point P1, which will become a puncture in, if all the cylinders were disjoint from this segment, then okay, then gamma I prime would be just would coincide with gamma I, would be isotopic to gamma I, and our map indeed would be the identity. So an interesting for me is the case when this segment intersects the cylinders. Okay, now, well, first of all, a standard thing, which of course requires some technique, but I will skip an accurate proof, that first, all the annuli AI can be made transversal, but by a small deformation, they can be made transversal to each other, and to the segment P1 times I. And besides, I would like that there are no triple intersections. So look, generally, if two cylinders if two cylinders are so sorry about triple intersections. One moment, it is not so easy. Yes, I don't want to do this. Okay. I only triple intersections about cylinders are allowed, but no. Well, what I would like to, it is not allowed that the segment P1 times I intersects two cylinders simultaneously. So all intersection points of P1 times R with the annuli AI are on different heights. Well, of course, it is easy to deform cylinders so that they intersect this segment in pairized different points, but it is not easy to deform the cylinders, so it is not easy to destroy triple intersections, and actually we do not want, it is not our goal to triple intersection between cylinders are allowed. Indeed, two cylinders intersect by a circle. A circle may intersect the third cylinder, and intersection of a one-dimensional and two-dimensional objects cannot be destroyed by a small deformation in three-dimensional manifold. Okay, but now, okay, this cylinder, this annuli AI can intersect each other, and the picture can be rather complicated. Yes, note that the curves gamma I are not disjoint, not necessarily disjoint. These are just they are not. The matter is that this K, of course, is not supposed to be a simplex. It is just some subcomplex. So it is allowed that it's several its vertices maybe not connected by edges, and actually we have rather complicated picture here. But I would like to achieve that, and this is and we would like to achieve the following, that the following condition holds. If gamma I and gamma J are disjoint, so if two curves are not disjoint, then we would do not want to make any restrictions on the intersection of the corresponding annuli. But if these curves are disjoint, then in this case there are only two possibilities. Then either the corresponding annuli do not intersect, or there is another possibility, or the corresponding curves gamma I prime coincide, and the intersection of the cylinders is exactly gamma I prime with 1. Look, indeed, it is possible I will draw another example by take. It is possible that two curves, say gamma I here and gamma k, this one was gamma j, but for instance gamma I and gamma k, it is possible that they become isotopic in Sgn-1. Sometimes it is possible that they are disjoint in Sgn and they become isotopic in Sgn-1. Then the corresponding curves gamma I and gamma k just coincide in this case. And then the cylinders cannot be disjoint from each other, but the claim is that in this case, the cylinders can be made disjoint except for the final moment of time, except for t equals 1. Okay, so this is not something. This condition is not true automatically. So it is our goal to achieve this. We will change the annuli so that to achieve this condition is satisfied. Okay. Now we proceed in the following way. First, well, okay, look on any pair of gamma I and gamma j as in this condition. So suppose that gamma I and gamma j are disjoint. If they're disjoint, then, and also they are transversal to each other, then not they, but the annuli are transversal to each other. So all unwanted intersections are just circles. All unwanted intersections, unwanted means that we allow all intersections between between the annuli that correspond to non-disjoint curves, and we allow this intersection at the last moment. All other intersections are called unwanted. And okay, just any if two-dimensional manifolds intersect transversely in three-dimensional manifold, then all their intersections are circles. In particular, all these unwanted intersections are also circles. And we would like to have induction by the number of such circles. So we would like to decrease the number of such unwanted intersections step by step, and then achieve that the two annuli are disjoint. Okay, we need to make a break now. Yes. Maybe it is a good time to do this before going into details. So let us have a 10-minute break, and then we proceed with the proof. Actually, I'm not precise here. I'm sorry. The situation is as follows. We have many curves, gamma 1, gamma k here. For any of them, we have this cylinder, and we would like to study we would like to avoid intersection of those cylinders that correspond to disjoint curves. We would like to measure somehow the complexity of the situation. So suppose that these cylinders intersect each other, and we would like to measure the complexity of the situation. And the first idea is indeed to take the sum over all. So, but we do not intersections between those those annuli that correspond to non-disjoint curves. It's okay. So we may, the first idea for the complexity is that we take the sum over all pairs ij such that gamma I is disjoint from gamma j. We may take the number of components of the intersection. I will write the number of unwanted components. This means that this component is allowed. If the intersection is like that, if the intersection is only at a final moment, then it's okay. We don't want to do anything with it. This is the first idea, but, and actually, actually, in the paper by Harrer, this is exactly what is written there, that we take such measure of complexity and we decrease it during certain procedures. The procedures described by Harrer actually help, so they actually simplify the situation. But as far as I remember, when I became ready to this lecture, I found out that in fact it is not completely true that this particular complexity is decreased. As far as I understand, it is possible that it increases, and we will discuss this later when I describe the movements introduced by Harrer. But the complexity which is decreased is as follows. Now look for on all these unwanted circles. Any this unwanted circle lies in two cylinders, AI and AJ. But it is also possible that this unwanted circle may intersect with each other. It is always possible that this AI, this gamma I, gamma J, it is also possible that there is some gamma K, which is also disjoint from gamma I, but maybe not disjoint from gamma J. So it is possible to have a picture like that. So here we also have gamma K, which is disjoint from gamma I, but not disjoint from gamma J. And we may have here some intersection, or it is also unwanted intersection between gamma K and between AK and AI, and it may intersect those circles, and there can be plenty of such situations. So as a result, any unwanted circle is decomposed by other unwanted circles into some arcs. Sometimes it is not decomposed, but sometimes it is decomposed. So as far as I understand, the correct complexity is the number of arcs of unwanted component. So any unwanted component we can compute as many times as the number of arcs is. And then it is actually possible to reduce the number of this complexity step by step, and to achieve that finally we avoid all unwanted intersections. Maybe the original complexity by Harrer still works, but I do not see any argument for this. Maybe so now I would like to explain what are the moves introduced by Harrer, how to decrease this complexity of the situation. So suppose that look on it, let C be an unwanted circle in the intersection of two cylinders. So we have the following picture: gamma I and gamma J are disjoint. We have these two cylinders, and we have here some circle of intersection. Just some schematic picture. Okay, there are two possibilities. How can a circle on a cylinder look like? There are two possibilities. It can be homotopically non-trivial in this cylinder. And then, of course, well, there are only two possibilities for a simple closed curve in a cylinder. It can be either homotopically non-trivial or homotopically trivial. Either it bounds a disk in this cylinder, or it is isotopic to the basis of the cylinder. And let us consider these two cases. First case, C is homotopically, but okay, C lies in two annuli. I'm sorry, I sometimes say cylinder, sometimes annuli. C belongs to two annuli, AI and AJ. So assume that C is homotopically non-trivial in homotopically non-trivial in one of these annuli, in AI, say. Okay, but now look, what does it mean? This means that C is homotopic to here AI finishes by gamma I prime multiplied by 1. Gamma I prime times 1 in this surface times I. It is homotopic to this guy just in the cylinder. This part of the cylinder, this portion of the cylinder gives a homotopy between this curve and the upper base of the cylinder. But then C is homotopically non-trivial. We know that this curve, all our curves are essential, so they are homotopically non-trivial. C is homotopically non-trivial in, again here. But look, in the second case, our circle would be homotopically trivial since it bounds the disk. It would be homotopically trivial in the annuli, and hence in this three-manifold. So we see that these two cases cannot mix with each other. So if we have the first case in one of the cylinders, then we also have the first case in the second cylinder too. So C, in this case, C is homotopically non-trivial in AG as well. But now look, so C is homotopic both to gamma I prime times 1 and gamma J prime times 1 in this look. This means that gamma I prime is homotopic to gamma J prime in this surface with n-1 punctures. Oh, okay, but actually this gamma I prime and gamma J prime, let us recall how the mapping psi was constructed. Under a mapping psi, if two curves lies in the image of psi, if two curves are obtained by psi, and they were homotopic here, then they are homotopic here as well. So this means actually that in this case, gamma I prime coincides with gamma J prime. So if this homotopically non-trivial situation occurs, this may only be in the case when, which we have already discussed, that two curves like that go to the same curve, gamma I prime equals to gamma J prime above. And here, somewhere here, I'm sorry, it is maybe I would like to draw it sometimes here. Here we have some. It is difficult to. Well, it is not difficult to draw it, but it is actually looks like that. This is one of the annuli. Actually, the situation is like that. It is another annulus. So this one is gamma I, this one is gamma J, this one is gamma I prime equals gamma J prime. And here we have this unwanted intersection, which is essential in both cylinders. So what to do if we have the following situation? actually, since let us recall that the intersection along this C is transversal. So if we look along C, then in the normal direction, we have the following situation. So this is AI and this is AJ. Just I would like to rotate this. It is not possible. Since we have level structures, so in fact, the situation is like that. We have C and we have AI, which goes like that, and we have AJ, which goes like that, and we have this level structures projection on the segment 0, 1. Okay, and now we can perform the following surgery. We can replace this cross along C by 2 arcs. This means that above C, we interchange the portions of the cylinders AI and AJ. So the new, here it is AG, here it is AI. After our move, this portion of AI becomes AJ, and this portion of AJ becomes AI. So above C, we interchange the portions of AI and AJ. The matter is why we can't do this. The matter is that these two cylinders still lead to the same circle. So our destiny, our goal is the same for both cylinders. So we can interchange them and no problem appears. Well, I'm sorry, only now I see one problem. It often happens in the proofs like that there are some hidden problems. I see one problem which actually wasn't discussed by Harar, and actually I saw it only now when I speak it to you, and actually I don't know at the moment how to resolve this problem. Look, okay, we always can do this, and of course we decreased the complexity of the pair IJ. Yes, of course we have reduced the complexity of the pair IJ. That's okay, since we delete this C. This C not anymore an unwanted intersection. We may have some all other unwanted intersections between I's and J's cylinders preserve, but we have one less unwanted intersection. And but actually we have the following problem. Just I would like to mention it. I do not know at the moment how to handle this problem. Suppose that we have some other curve here, some other. Actually, when I prepared to this lecture, I partially saw this problem, but saw a part of this problem, and I thought that this dividing into arcs helps us, but as far as I understand, it doesn't. Look, you may consider a curve which get gamma k. It is possible that there is a curve gamma k which is disjoint from gamma j, but is not disjoint from gamma I. Yes? Then intersections of gamma j with gamma j with gamma k are unwanted. We would like to delete them. But intersections of gamma k with gamma I are not unwanted. We allow them in any amount, and we do not want to delete them. And then it is possible that this cylinder gamma k has plenty of intersections. This cylinder AK has plenty of intersections with AI above the circle C. So if there are such intersections, they do not affect the complexity, since they are allowed. But once we replace these portions of gamma I and gamma of AI and IJ, these intersections become intersections with gamma J, which are not allowed, and complexity may increase very much.
Сейчас, может, тогда еще один, может быть, другая проблема, это не проблема. Вот если у нас пересекается какая-нибудь кривая, другой unwanted circle, пересекается с C, то там же появится, скорее всего, две точки пересечения после такой.
Не, у нас C пропадет. То есть как раз я понимал, что когда кривые пересекаются с C, то после такой штуки их количество, например, может измениться, причем в обе стороны. Но количество дуг уменьшится, потому что C пропадет. C больше не является unwanted circle.
Окей.
Поэтому этой проблемы нет. Вот я как раз эту проблему я заметил при подготовке к лекции, и я ее победил. Вот. А вот ту проблему, которую я сейчас озвучил, я, к сожалению, заметил только сейчас. Поэтому вот так сходу я не знаю, как ее побеждать. То есть вот этот вот цилиндр гамма-К, которому разрешено пересекаться с гамма-I как угодно, он может вот там вверху очень сильно с ним пересекаться. А когда мы эти кусочки меняем, то вдруг раз и оказывается, что им пересекаться больше нельзя. Ну, понятно, сложность сильно возрастает. Давайте это пока замнем. Вот. И как бы на идейном уровне доказательство вроде должно работать, но может быть в каком-то смысле работает, если идти сверху вниз, но не очень понятно, что такое сверху вниз, потому что эти нежелательные окружности могут как угодно пересекаться друг с другом. В общем, well, I proceed. Here there is a gap, as far as I understand, and I will try to fill it till the next time. You may also think about how it is possible. I don't know whether it is easy or not. So, but ideologically, we would like to do such simplification moves, but it is a tiny, complicated question by why they actually simplify. Let us consider the second case. But still, it is not everything is good here. The second case B is when this unwanted intersection is homotopically trivial. And again, these two cases cannot mix, so it is homotopically trivial both in AI and in AJ. Look, for this particular pair of I and J, there can be several unwanted intersections. There can be plenty of these circles. Let us choose those which is innermost in AI. Innermost in AI and innermost in AJ are completely different story, but let us choose C to be innermost in AI. So forget about all this. And this is C. It bounds a disk DI here. And I'm sorry, I draw it like that. I don't want to draw intersecting cylinders. I just draw it schematically. This is the same C, and it bounds another disk DJ here. Well, actually, again, the same.
Можно предыдущий вопрос, проблема еще один вопрос. Но вот если у нас такая ситуация, это же означает, что мы вообще никак не можем избавиться, даже чисто теоретически, от пересечений АК и АИ и АГ. Но они, в смысле, всегда будут. То есть у нас какое-то пересечение, оно насколько вообще unwanted?
Значит, смотрите, вот то, что Харрер написал, несомненно, хорошо работает, если мы для данной конкретной пары ИЖ хотим все.
Нет, я понимаю, я про то, ну вот, допустим, мы даже добились успеха, вот мы, значит, брали все unwanted circles.
Это я сейчас объясню, почему это хорошо.
В смысле, у нас же как бы гамма-К по-прежнему пересекается с...
Да. У нас... Нет.
То есть там такая кривая, да, получается, а не цикл? Или...
Почему? Кто пересекает?
Моя проблема в том, что я не понимаю, видимо, что такое unwanted circles.
Unwanted circle – это пересечение между цилиндрами, которые соответствуют не пересекающимся гамма-А и гамма-J.
Не пересекающимся изначально?
Изначально.
Но тогда у нас есть пересечение, ну, то есть у нас есть цилиндры, которые кривых, которые изначально не пересекались, а потом пересекаются.
Ну вот мы такое и стараемся убивать.
Но они, в смысле, в итоговой картине, как конечной, начнут пересекаться. Не в процессе, а вот и в итоге. Вот это же ровно наша проблема сейчас.
Я не понимаю, мы стараемся уменьшать количество.
Вот, да, вопрос такой. Вот, как бы, есть у нас ситуация, когда гамма-J и гамма-К не пересекаются, а гамма-J' и гамма-К' пересекаются.
В этом случае мы не стремимся избавиться от конечной. Вот unwanted – это все, кроме вот такой. Вот в конце им пересекаться можно.
Да, но там получается тогда не circle, а arc такая. В смысле, они вот... Ну, потому что, а вдруг они не совпадают, но пересекаются?
А вот так не бывает. Если гамма, well, if gamma I and gamma J are disjoint, then gamma I prime and gamma J prime are either disjoint or coincide.
Да, это про... то все, я
Да, то есть,
поняла проблему.
If this is yes, this is important observation. If gamma I and gamma J are disjoint, then there are only two possibilities. Then either gamma I prime and gamma J prime are also disjoint, or they coincide. It is not hard, but the hard part is that we have this, we would like the same for annuli, almost the same, that if gamma I and gamma J are disjoint, that then either the whole, in the first case, we would like that the whole annuli are disjoint. In the second case, we would like that the annuli are disjoint up to the last moment. In the last moment, they of course intersect since the curves are the same. So we would like to delete all other intersections between such annuli. And note that we don't want to delete any intersections between annuli that correspond to curves that initially intersect. If gamma I and gamma J initially intersect, then all intersections about annuli are allowed. That's okay. Well, unfortunately, here Harrer suggests the following, and as far as I remember, as far as I understand, the same problem appears. That okay, we may here, if we look on C, alone C, then the situation is I'm sorry, C is a circle, but for my goal, it is convenient to draw it as a zero-dimensional circle. I'm sorry, this is just for simplicity. So this red one is AI, this blue one is AJ. In this situation, Harrer suggests now we cannot interchange above portions of AI and AJ since they lead to different circles. But what we can this is disk DI, this is disk DJ. We can replace the J by the following. We can replace the J by DI. Again, this simplifies the complexity of this particular pair. But again, there is a problem that it is possible that AI is allowed to intersect certain AK, and so the problem is the same, that there can be some AK here which is allowed to intersect with AI such that gamma I and gamma K are not disjoint, but gamma J and gamma K are disjoint. So again, we have a problem. I'm sorry, I do not know how to solve this problem immediately. But okay, here there are some ideas which it is a big question whether they work or not. I'm sorry for this, but actually maybe it is useful to feel that there are plenty of possibilities to make such mistakes in this field. Unfortunately, there are plenty of such gaps, even in very good proofs. So you always should be careful about them. And okay, now I would like to explain why do we want this condition star to be satisfied. So suppose that we have achieved this. I think that maybe this can be made a good proof by some more delicate study. So suppose that we have do this and this condition is satisfied. Now, how does this helps us? Look, now again look on this picture in total. We have this surface as gn minus 1 times segment. We have this annuli, which now intersect as it is prescribed here. Now look on some level. Yes, and there is one more important thing. There is here a point P1 and there is a segment P1 times I, which intersects annuli transversally infinitely many points, and it doesn't intersect to annuli at the same time. So let us choose a non-special level. Non-special, I mean that such level that there are no intersections of the segment with annuli, with the annuli on this level. So we take any level except for finitely many that contain such intersections. Then this level, let us denote it by ST. It intersects our annuli in certain circles, which we denote by gamma I of t. These are annuli. Annuli are embedded so that they preserving the level structure. So this intersection is indeed an embedding. This intersection with the level ST. So in this level ST is of course homeomorphic to the surface of genus G with n-1 punctures, and we have this collection of simple closed curves. And look, what can we say about these simple closed curves? These simple closed curves are isotopic to original curves, but they are isotopic in SGn-1. If we now add this puncture P1, then gamma I of t, yes, gamma I of t, they do not pass through P1. So if we add this puncture P1, then we get a well-defined collections of curves on SGN on surface. So look, gamma 1 of t gamma n of t, gamma k of t, can be regarded as curves on ST with puncture 1 deleted, which is the surface with n punctures. And one more important observation, that since we know about the intersection of the anguli, we also know this following, that gamma I of t and gamma j of t are disjoint whenever the initial curves, this is what we try to prove, whenever the initial curves are disjoint. So what does it mean? This means that at any moment of t, look, now let us recall that we started from a finite subcomplex of C hat, or of C hat of SGN. The simplest of this subcomplex spanned by certain collections of curves that are disjoint. But if some collection of curves was disjoint in the original moment of time, then for any moment of time t, the corresponding curves are disjoint as well. So we have the complex for any t, we have also the subcomplex, the corresponding subcomplex formed by where the curves, just these vertices are replaced by vertices gamma 1 of t, gamma k of t. This can be different subcomplex, since our curves are isotopic only after forgetting of a puncture. Before forgetting of a puncture, they are not isotopic, but they are disjoint whenever these curves are disjoint. So this subcomplex is well defined. So in any non-special moment of time, we have a subcomplex here. Yes, why it is in C hat? It is obvious, since after deleting P1, these curves are essential. So we are actually not only in the C of SGN, but in the head of SGN. And of course, this subcomplex does not change. It cannot change continuously, so it doesn't change when we are on an interval between two consecutive special moments of time. So we only need to see what is happening at certain consecutive moment of time, or at certain special moment of time. So if we have this P1 times I, and at some moment it intersects transversely, some cylinder AI, and we look on this only locally. What is happening here? Locally, we have the following picture. We have a curve gamma, let this be time t0. We have curve t0 minus epsilon below this point, and we have curve gamma I of t0 plus epsilon above this point. All other curves do not change. So only gamma I, all other curves do not change when we pass through this point. And it is not hard to see that gamma I in fact changes like that. So the situation is like that. Gamma I was certain curve. Oh, sorry. The curve. Sorry, the curve cannot be like that. The curve should be closed. So we have something like that, and here we have some punctures, and here we have puncture P1, and this one is gamma I before we pass through a puncture, and actually after there will be the same gamma I, but it will just pass through P1, so it changes like that. This is gamma I of T0 plus epsilon. And of course, in this situation, we may easily make these two curves disjoint. We just go around this curve. I'm sorry for this. So we just go. Sorry. I choose too difficult situation. It is better to draw something easier. Well, here we have P1. So if gamma I before the puncture was like that, then gamma I after the puncture goes like that. So it is disjoint from gamma I before the puncture, and it is disjoint, and it is disjoint from all gamma j's, gamma j of t, of the corresponding t, such that gamma I was disjoint from gamma j. And so the main claim is that, well, actually, each of these kt can be thought as over embedding of k into the head of SGN. Each of these kt is a copy, not necessarily embedding. Actually, it is a map, since it is possible that some gamma i's finally become the same. So I just would like to say that this embedding at the moment of time T0 minus epsilon is homotopic to this embedding of the moment of time of T0 plus epsilon. The matter is that this is as following. We have these vertices corresponding to all gamma j of T0. They do not change. And we have this particular vertex corresponding to gamma I of T0 minus epsilon. And we have this vertex after time T0. And we see that these two curves are disjoint. So these 2 points, these 2 vertices of the complex are connected by an edge. And in all other simplices, whenever the simplex is present, if this simplex is present in K of T0 plus epsilon, then the corresponding simplex is present in T0 minus epsilon, and this simplex of one higher dimension is also a simplex of C hat. And since all these curves are disjoint. And so we can easily deform this subcomplex to that. Just moving this vertex linearly and preserving all other vertices. Okay, so I'm sorry for actually I didn't expect that the proof contains some problems, but it turns out that it does. So up to this modulo this problem, we have finished the proof, but okay, actually it is not easy, and there are some problems. I will try to handle them till the next lecture. And now, well, all of this was about the first claim, why our complex is homotopy equivalent to a complex of sufficiently small dimension, namely of this particular dimension in each of these situations. Now we would like to prove the second claim, that this complex is connected with the corresponding level of connectedness. So the claim is next claim says that the curve complex of SGN is n-1 connected, where n capital equals 2g minus 2 if g, let us start with another, 2g minus 3 plus 1 if both g and n are positive. It is equal to 2g minus 2 if g is positive and n equals 0, and it is equal to n minus 4 if g is 0. Okay, first of all, before proving this, let us say that sometimes our claim is nonsense. For instance, for S02, n minus 4 becomes minus 2, so it is something like complete nonsense. But I would like to say that -1 connected is not a nonsense. -1 connected, it is convenient to understand that it is non-empty. So this the only situation when the claim is complete nonsense is S01 and S02 and S03. We have here n-1 connected. So in these three situations, actually our complex is just empty, and this claim is complete nonsense. So we do not want to prove anything about empty complex. But in all other situations, the complex is non-empty. And actually, if we look precisely, the only situation when we cannot guarantee zero, that zero connected is just connected. Zero connected is just connected. One connected is simply connected, and so on. The only situations except for these three are completely non-interesting. There are two situations, not two, three situations. Sphere with four punctures, torus with a closed torus, and torus with one puncture. In all these situations, the corresponding formula gives us 0. This number n is 0. And so our complex is non-empty, but not connected. Non-empty, but non-connected. Actually, the claim doesn't say that it is not connected. It is say only that it is non-empty, but it is easy to check in each of these cases. Then actually it is not connected. Any two essential simple closed curves in one of these three surfaces intersect. So there are plenty of, there are infinitely many simple closed curves, but any two of them intersect. So the complex is just a discrete number of points. In all other cases, this complex is at least connected, according to this claim. Well, now, actually, I'm sorry, I should told this immediately when I would like to return to some point in the previous lecture. In the previous lecture, I described how we make, sorry. Well, we have this situation when we understand how the complex for n punctures is obtained from the complex for n-1 punctures. And it is obtained as, I just would like to copy this part. When we pass from the surface of n punctures to a surface with n-1 puncture of the same genus, then we have already proved, but with a mistake, but still, that this is a homotopy equivalence. When we try, so this complex C hat is homotopy equivalent to the complex of the same genus of the curve complex with the same genus and one less puncture. And when we try to restore to construct the total C of S from C hat of S, we need to proceed as follows. We choose any C of S. If a vertex belongs to C of S but doesn't belong to C hat of S, then it contains a curve which encloses exactly two punctures, one of which is P1, and we have discussed that two of such curves, first of all, there are infinitely many of such curves, and second, two of such curves are not if they are different, they intersect, so they cannot be disjoint. Two curves of this type cannot be disjoint. So look, if for each of such curves, let it be beta, for each of such curves beta, we add this, we attach a cone over the hat of S with this vertex beta. And these cones are attached separately. No two of these curves are connected to, no two of these vertices are connected to each other. So from the homotopy point of view, we see that this C of S is homotopy equivalent to the following. We take infinitely many cones with the same base C hat and glue them along the common base. In other words, this is the join of C hat of S with infinitely many points. So this is discrete topological space consisting of infinitely many points. But up to homotopy equivalence, this is the same as C of S0, since we have proved that phi is at homotopy equivalence, the same, infinitely many points here. Okay, but it is easy to see that once, if we take join with infinitely many points, or if we take join with a discrete set of points, then connectedness is increased by 1. So if C of S0 is R connected for certain n, then C of S is R plus 1 connected. Just this is a general situation. If we take infinitely many points, actually can be thought of as wedge of zero-dimensional spheres. If we take wedge of zero-dimensional spheres, connectedness is increased by 1. So what I would like to say, that this claim, the induction by n in this claim is more or less obvious. So it is sufficient to accept maybe for the situation with the station between n equals 0 and n equals 1 is somewhat special, since there are no such curves beta, except for this case. The induction on n is obvious. So we suffice to prove our claim 2. It is sufficient to prove claim 2 it is sufficient to prove claim 2 only for n equals 0 and n equals 1. But look, if n equals 0 and n equals 1, then here we have the same number 2g minus 2. And besides, in the situation when n equals 1, this c hat just coincides with usual curve complex. So we have already said this, that we have this homotopy equivalence. So actually, it is sufficient to prove it only for n equals 1. And it follows for n equals 2, 0, since this is up to homotopy equivalence, this is the same complex. So it is interesting, but n equals 1 is easier than n equals 0 here. Yes, there is one special case. The special case is genus equals to 0. When in this special case, we cannot use n equals 1 for the base, since it's complete nonsense. We have just empty complex. In this case, we can use for the base the case of S04. So for g equals 0, base is n equals 4. For n equals 4, our claim is that this complex is -1 connected. That is non-empty. And it is actually non-empty since on the sphere with 4 punctures, there are essential curves. So it is non-empty. Hence, on the second step, we take the join of an non-empty complex with infinitely many points, we get connected complex. And on the next step, we get simply connected complex, and so on. The induction goes. So the only situation is we need to prove our claim for SG1 where G is positive. And what we need to prove? We need to prove that SG1 is to G minus 3 connected. Indeed, we would like to prove that it is n minus 1 connected when n is to G minus 3 plus 1. So it is exactly, we would like to prove that it is 2G minus 3 connected. In case G equals 1, it is -1 connected, and we need to prove that there is an essential curve on the torus. This is true, so it is true for G equals 1. So we may assume to avoid such special cases, we may assume that G is at least 2. Here, the idea is, well, there are several possibilities to do this. I like the following idea. We may understand topological properties of the curve complex, thinking of it as a subcomplex of the arc and curve complex. Here I would like only one. So recall that we have arc and curve complex where vertices are both arcs and curves, simple closed curves, and again simplices are spanned by disjoint arcs and curves. And about this complex, we know that it is contractible. It is exactly, we would like to have 1 here rather than 0, since there it is not well, there is no arc and curve complex, is just curve complex for closed surface, so we have no such possibility to do like that. And now look how this is subcomplex of the overcontractible complex. And now we would like to study how this contractible complex is obtained from this complex. And analyzing this process, we understand something on connectedness of the original complex. Look, there are, we need to look on those simplices of the arc and curve complex that are not contained in the curve complex. So a typical situation is like that. We have this simplex. This is a simplex of arc and curve complex, and say this blue subsimplex belongs to the curve complex. And we would like to add these simplices consecutively. So all simplices which are entirely in the curve complex are there from the very beginning. Then we add simplices. Let the simplex be added. We add simplices at that belong to the arc and curve complex. I just denote this surface by S, but do not belong to the curve complex. We add them consecutively by the parameter is the number of vertices of eta that correspond to arcs. So these are those vertices that correspond to arcs and not to curves. There are, in this example, there are 2 vertices which correspond to arcs. So we first add these simplices, and only then add the total simplex. Well, okay, and each time we add, I'm sorry, I have only 5 minutes. Yes, maybe I will say some idea, and maybe I will. Look, when we may first add vertices, add all simplices that contain exactly 1 arc, which is not a curve. So we add this arc and all simplices like that. Let us consider this particular step in more details. So we start with complex SG1, and we add certain arc alpha, and we add all simplices that contain this arc, and all other vertices of this simplex are curves. These are curves. So we add cone with apex alpha over some subcomplex here. And let us try to understand what is this subcomplex. This subcomplex seems to be very similar to the curve complex of, okay, we will consider S with alpha deleted. Look, how does it look? Say we take such arc alpha. When we delete alpha, we get, okay, we may get a closed surface or not closed surface, connected or not connected surface. If non-connected, then just we take join of the corresponding to curve complexes. But the matter, the most important thing is that L, so L is spanned by, L is spanned, but in any situation, if we take genus G surface with one puncture and we delete, actually what can happen? We may either, if this arc doesn't separate the surface, then we get the surface of smaller genus with two, of smaller genus with two punctures, or we have union of two surfaces with each with one puncture. But look, this is not the curve complex. This L is not a curve complex. The matter is that here we have such curve which goes around our arc and which can be essential. But if we look on this curve, it is essential is in the original surface SG1. But if we look on this curve here on SG minus 1, 2, then it is a curve around one of the two punctures. So here it is inessential. So it is not allowed in the curve complex. So in this L, we have this curve which is allowed in the curve complex of the original. And so it belongs to L since it is disjoint from alpha, but it is not allowed in the curve complex of this deleted surface. And look, this curve, let this curve be beta. This curve beta is disjoint from any curve which is disjoint from alpha. So if alpha is disjoint from some simple closed curve gamma, then beta is also disjoint from gamma. The matter is just beta lies in an arbitrarily small neighborhood of gamma, of alpha. And so actually, in this situation, this complex L is itself a cone. With apex beta, and so is contractible. Well, so the situation is as follows. We start from this complex, and actually we add cones, but we always add cones over contractible complexes. So the topology doesn't change. And the same proceeds up to the very last moment. The very last moment is when I will be more precise in the next time, but if we have several arcs, then it is possible that they decompose our surface so that several arcs can decompose our surface, for instance, as a 4G gone, usual 4G gone. And then this curve, in the very last moment, this curve beta becomes essential, since it bounds the disk here. So, but at that moment we will compute some dimensions and understand that this contractible complex is obtained from this complex by adding cells of dimension 2g minus 2. And this will prove that the original complex was 2g minus 3 connected. So this is just the idea. I have no time to, I'm sorry for this is because of today's I was late with the beginning of the lecture and I have no time to finish it now. So next time we quickly finish this and then we proceed. Actually, now we come to a time when we have some amount of complexes where the group acts. We know something about topology of this group, and now we will be able to understand many pretty things about the mapping groups. Okay, that's all for today. If there.
Спасибо.
Александр Александрович, пользуясь случаем, я хотел напомнить про тему курсовой.